Well, greetings, mathletes, and welcome back. We're going to be talking about implicit differentiation today. Now, implicit differentiation, aside from being a mouthful, is actually just an application of the chain rule. And what we're actually doing, and you'll get a feel for this once we start seeing some examples here. Um, but where this gets applied is places where you cannot actually separate y out as a function of x. So basically, equations that aren't actually functions. It's how we take derivatives and find the change in y with respect to x for things that cannot be written explicitly as a function. So let's go ahead and take a look. We'll take a look at our first example here. And this is more of an example of why we need to do this at times. And so let's say the equation I have is a circle, right? And uh, let's make it a circle of radius 5. So the equation here would be x squared plus y squared equals 5. Well, this is clearly not a function. It doesn't pass the vertical line test, right? I hit 2 points here. And in fact, that is actually what the problem is. Normally, we want to take a derivative at a particular x value. But you notice if I pick an x value here, for example, if I pick this to be x equals 3, right? Let's say that's a 3. Well, there are two different y values involved, right? And so there are two different derivatives at the point x equals 3. So what you end up needing is a y value also so that you know which one you're picking from. And there are functions out there where it's more than 2 points, right? We could actually just carve this down into the upper half of the circle, take the derivative of that, the lower half of the circle, take the derivative of that. Um, but it gets much, much more complicated when you have more than two places that it crosses. So what we're going to be looking for here is we want dy dx. And so we're going to be finding this, but for this first example, at least, I'm going to use a specific point. So this is the notation we use if you want to evaluate something at a particular point or a particular value. So I want to find dy dx evaluated at the point 3, 4 for this equation. Okay, well, this is how we go about doing it. We don't bother trying to solve for y. We actually leave it exactly how it is. And what we're going to do is we're going to take the derivative of both sides. So we're going to apply a ddx to both sides of this. And then we need a ddx of 5. Right? Well, we know how derivatives work. We're going to be taking derivatives all the way across. So I need ddx of x squared, and then I need ddx, oops, try that again, ddx of y squared, and you can see there's going to be a problem here because this is a y and that I'm taking the derivative with respect to x. So this is where it's going to come out. And then the right-hand side, which hasn't changed. Okay, now, if I'm taking the derivative with respect to x, if that's a dx there, then I can just take a normal derivative. This term is now 2x. But if I'm taking a ddx and it's a term with a y in it, we have to treat y as if it's a function in and of itself. So that means we need a derivative of the inside also. So I can start out just by taking a regular derivative of 2y. That's a derivative of the outside, right? Now the derivative of the inside is the derivative of y with respect to x, because we're assuming y is another function. But since we don't have that, what we do is we just write dy dx because we don't have it, right? We don't have that function of y yet. And then ddx of 5 is 0. Now I want to, oops, that actually should have been a 25 if it was going to have a radius of 5. Oops. In any case, what I do want to point out is that with a circle, you notice it doesn't matter what the radius was, it always goes to 0 when you take that derivative, which is kind of interesting. Um, Now, we're not done finding dy dx yet. What we need to do is get the dy dx by itself. And so what we're going to do is just treat it like another factor in this term. So I'm going to move the 2x to the right-hand side. So this would now be 2y dy dx equals negative 2x. And then I'm going to divide the 2y over. So I get dy dx is equal to negative 2x over 2y. And I can cancel those 2's out to make this negative x over y. And so if I want to, now, I still haven't evaluated this, right? But if I take dy dx and I evaluate it at 3, 4, what I get, I just need to plug this in. So it's going to be negative 3 over 4. So it's negative 3/4. Right? So we just found the slope, right? If this was at 3, the point 3, 4 would be this one up top. And what we just did was we found the derivative of this. Right? We found the slope at that point. And the fact that that dy dx includes y, the reason it includes y is because that is what allows us to differentiate between this point and this point, right? I would be using the negative y value. It would be 3 negative 4 if I was in the bottom part. Okay, so that's our first example, and that's just kind of showing the motivation of why we're doing these things. These are for things that aren't functions. Oftentimes, it is way easier to use implicit differentiation than just regular differentiation. Okay, so and also the other thing is that basically, whenever you're dealing with these things, whenever you're taking the derivative of a term with y in it, once you get down to the point where you're taking the derivative of that y, you write a dy dx. And that's basically what happens each and every time. So let's take a look at another example here. This one's going to take a little bit more room up, but it'll be fun nonetheless. So we got 2xy plus y squared is equal to x plus y. And we want to find dy dx, right? So we want the change in y with respect to x. That's what we're looking at right now. Okay, and we're going to find real quick that this implicit differentiation, it works with all the other rules we have. So the power rule, the product rule, the quotient rule, and surprisingly, the chain rule too. It works with all of those things. And so we're just going to go through this term by term and take the derivative of everything. Then we're going to try to get all of our dy dx's together in the same spot and put everything else on the other side. That's basically the drill. So to start off with, I want to look at this first term as two different functions. So if I'm going to take the derivative of this, it's going to be the product rule. So it's going to be the first times the derivative of the second. Now the derivative of y by itself, dx, is dy dx. Right? So that's the first times the derivative of the second, or 1 d2. And then plus 2d1, 2 is just y, and the derivative of 2x is 2. So this is y times 2. Right? And so that's our first term. This part right here is the derivative of our first term. This right here. Okay? Now, the second term, the y squared, this is where the chain rule comes in because it's housed inside of a square function. So we take the derivative of the outside first, which makes this a 2y, and then the derivative of the inside is just the derivative of y. So that's our dy dx. Basically, when I was a student, one of the things I did was I just remembered that whenever I take a derivative of y by itself, it's a dy dx, right? And that's the one thing that got me through here. Okay, now the other side, the derivative of x dx would be 1. and the derivative of y dx is dy dx. Ooh, we walked through all of that stuff. Okay, let's actually clean it up a little bit here. So I have 2x dy dx plus 2y. Now the reason this 2y doesn't have a dy dx on is because we didn't take the derivative of the y. We only took the derivative of the x here. And that's what gave us the 2. Okay, and then that's plus 2y dy dx equals 1 plus dy dx. Okay, so the goal is to get all the dy dx's onto one side and everything else on the other. So I'm going to move all the terms with dy dx over to one side. So it's really, I just need to move this one to the other side and then move the 2y back over here. So I'm going to subtract 2y from both sides and subtract dy dx from both sides. So that gives me 2x dy dx plus 2y dy dx, right? That's this term. And then I subtract the dy dx over, minus dy dx equals, and then I subtracted this 2y to the other side, so it's 1 minus 2y now. Okay, if you need to go back and look at that carefully, back it up and just pause at each step and make sure you understand it. Okay, now we have a dy dx in every one of these terms. That means we can factor it out. So that leaves me with a 2x plus 2y minus 1 equals 1 minus 2y. And then from here, we can just divide this term over. 2x plus 2y minus 1, 2x plus 2y minus 1. And if we just go ahead and put it all together now, I get dy dx is equal to 1 minus 2y over 2x plus 2y plus 1. These things can get very tedious. You really have to slow yourself down and make sure you understand everything you're putting down. It's very easy to get lost in the algebra in these. So good bookkeeping is very important with this. Make sure you understand where every step came from, because it is so easy to lose pieces or to accidentally put extra pieces in with this kind of a thing. So this is really an exercise in being very patient with yourself. Okay, once you get the algebra down, and really that's where the biggest problems come in, is with the algebra on this. Once you understand the algebra, these go pretty quickly, but they are still tedious. You have to be careful not to rush, because it's very easy to make a sign mistake or some other kind of very small mistake in these. All right, so let's go ahead and take a look at the next one. We'll mix in some trig this time just for fun. So let's see here. So let's say we get xy is equal to cotangent. That's not cotangent. Let's try that again. Cotangent of xy. Right? That's kind of an interesting one. And we want to find dy dx. And so in any case, all of the stuff we've learned still applies, right? And you actually have all the tools you need to get through this. It's just it's a new situation right now. See what you can get through on your own. Go ahead and pause it here and see if you can deduce everything you need to do in here. And then we'll take a look at it together and see what you get. Okay, I'm assuming you've paused it. You've already taken a stab at it. So the idea is that we want to apply a ddx to both sides, right? Right, we want to take the derivative of both sides of this. So with the first side, it's x times y, so that's a product rule. So I need the first, which is x, times the derivative of the second. The derivative of y is dy dx, plus the second, which is y, times the derivative of the first. And you notice, I just want to point out, if I take the ddx of x, what I end up with is dx over dx, which is 1, right? So I just want to point out that we really are being consistent here. we're just using the differentiation rules more directly in a formulaic approach, but it really is, it really is taking exactly what you think. So d dx of x now is just 1. So I'm just going to leave that there. So it's x times dy dx plus y for the left-hand side. And then over here, now I have a composition, right? I have xy, and then I have cotangent. The derivative of cotangent is negative cosecant squared, right? So if I start with the derivative of the outside, it's negative cosecant squared of xy, right? Now, because I'm using the chain rule right now. So that's the derivative of the outside. The derivative of the inside would be d dx of xy. Well, we already did that, right? We did that in our first step. So we can go ahead and write that down. So we have x times dy dx plus y is equal to negative cosecant squared xy times, now it's the derivative of x times y, which would be, since we just did this, it's the left-hand side. Where'd it go? Oh, x times dy dx plus y. Okay, and so what we need to do is we need to get all the dy dx's in the same spot. So what I'm going to do is I'm going to distribute this cosecant squared here so I can get a hold of this stuff. This one's going to take a little bit of work. And so if I apply the negative cosecant squared to the first term here, that would be, let's see here. Yeah, I'll just write it that way. Negative cosecant squared xy times x dy dx. And then the next one would be plus y times negative cosecant squared xy. Okay, now this is the term, this dy dx, this is the term I need to get over onto the other side. So I'm going to swap the terms around. So I'm going to add this cosecant squared xy times x dy dx to the other side here. And I'm going to subtract the y over. So now I have x times dy dx plus cosecant squared xy times x dy dx, right? And then on the other side, I move that y over here. So this would be, let's do negative y cosecant squared xy, and I'm subtracting the y, so that would be minus y, right? Oh, this is getting real messy. I'm running out of room real fast here. So if I pull the dy dx out of both terms here, it would be x plus x cosecant squared xy equals negative y times cosecant, blah. Oh, hell with it. Negative y times cosecant squared xy minus y. Right, and you can see from here, all I have to do is divide this x plus x cosecant squared xy onto the other side. And what I end up with is that dy dx is equal to negative y cosecant squared xy minus y over, and then now we're just going to include this part, x plus x cosecant squared xy, right? And there's our derivative. So that took quite a bit of work, and you notice how tedious it got. Actually, if I had written down every little step that I had done, I would not have been able to finish this on one page. Um, okay, so you need to make sure that you're on top of the algebra. Sorry, it feels awkward at the end of these problems. I keep wanting to pause and ask, hey, are there any questions? But no one's going to ask me questions right now, I don't think. All right, so let's go ahead and clear this out. Okay, now for our last example, I want to look at finding a second derivative using this. Now, normally when you have a function, right, something that can be written explicitly, right, I can take my first derivative using my normal rules. And if I want a second derivative, I just reapply those rules to the first derivative, right? So use the power rule, whatever, right? And I can take a second derivative. Now, with implicit differentiation, it's a little bit different. Um, Oftentimes, you have to take a first derivative and use the results from the first derivative somewhere in the computation of the second derivative. So let's go ahead and take a look here. So there it is. Let's say I have 2x cubed minus 3y squared equals 8. Okay. Um, so we want to find d squared y over dx squared, right? That's the notation for the second derivative. So we need to find the first derivative first. We need dy dx first. So let's start there. We'll have to use implicit differentiation here, because this isn't a function of y isn't an explicit function of x. So if I take the derivative of the first term, there's no y's in there. So I can take this and say this is 6x squared just using the power rule. Now, what's nice is there's no x's in here. And we haven't seen an example of taking the derivative when there's not any x's in there. It actually works out really nice. You use the power rule or whatever rule is apparent, right? So this would be minus 6y. And then we have to do the derivative of the inside, which is just y. So it's just a dy dx. So if there's no x's in the term, take the derivative and slap a dy dx on the end. Right? Works out pretty good. And then the derivative of 8 is 0. Okay, so this one's not too bad. Looks like we can isolate this pretty quickly. We'll subtract 6x squared over. I get minus 6y dy dx is equal to negative 6x squared. And if I divide by negative 6y, I get that dy dx is equal to x squared over y, because the 6's cancel. Okay, so we have one result, and I'm just going to jot this down over here in the corner because I'm going to need to get rid of a lot of this stuff. So dy dx is equal to x squared over y. So we need that result because we're going to have to take that derivative also now. So actually, I'll just do it this way. Okay, so now we need the derivative of x squared over y. And, well, that's a quotient, so we need the quotient rule. So it's low d high. So low would be y. The derivative of x squared is 2x minus high, which is x squared, d low, which is dy dx, over the square of what's below. So it's over y squared. And this would be, since we're taking the derivative here, this is d squared y over dx squared. Okay, let's clean it up a little bit. So d squared y over dx squared is equal to, let's see, that would make that 2xy minus x squared times dy dx over y squared. Well, we really don't want the first derivative housed in the second derivative, right? I mean, this is a problem, this thing hanging in right here. We want this totally in terms of x and y. So this is where we use the result from the first derivative. We know what the first derivative is. It's x squared over y. So all we have to do is plug that in. So if we do that, I end up with d squared y over dx squared is equal to 2xy minus x squared. But this time we're going to put in dy dx, which is x squared over y. And that's over y squared. Well, let's simplify this term a little bit. So that would make it 2xy minus x to the fourth over y squared. And, you know, it's really not very customary to leave fractions in fractions. So one of the things you can do is just multiply the numerator and denominator by the common denominator. And so since that's a y, we're going to multiply top and bottom by y. It'll cancel this one and make this one squared. So we end up with 2xy squared minus x to the fourth over y cubed. And this would be our second derivative. And you notice what we did though. We found the first derivative. We had to save that result, even though we took the derivative of it again. And we ended up having to plug it back in. Now we're going to have to do this later on, especially when we start learning the reverse operation for the derivative, which is the integral. You end up using a lot of your previous results in future computations. So you want to remember that all this stuff is very, very, very connected. Everything that you come up with can be used later on in the problem. All right. So that about covers everything that we needed to cover today. The next lecture is also going to be an application of the chain rule. It's going to be more of a physical application. But nonetheless, until next time, keep your pencils and your wits sharp.